Okay, so it's a joint paper with Christian Franck. It's about testing the existence of moments for for GARCH-type processes. And let's start with some properties of financial time series. So a standard assumption is that prices are non-stationary, while returns or log returns are strictly stationary. But there is no consensus concerning, even if such series are known to have heavy tail marginal distribution, there is no consensus concerning the existence of moments. At which order do such moments exist? Some researchers argue that stock returns don't admit fourth order moments. Some even question the existence of a finite variance. So I don't need to insist on the fact that existence of moments is central to many statistical applications. Many statistical tools may become invalid without the existence of appropriate moments. For instance, using the expected shortfall in risk analysis requires finite fourth order moments. Also, some estimation methods may require the existence of some moments. Even if for the QML estimation, for pure GARCH models, we don't have such moments. But for instance, if you have an ARMA GARCH model, you need some moments to exist. So testing stationarity of financial series has been already tackled in different ways. So here I give some examples of non-parametric ways to tackle this issue. A related issue is about testing strict stationarity. So here in the framework of GARCH-type models, so there are some papers, and I will, in this paper, consider this framework. So in the first part of the paper, of the talk, I will consider a standard GARCH model. And so this first part is already published, in fact, or close to be published. And the second part is more ongoing research, and it's about tests for augmented, so generalized GARCH 1-1 models. So let me first recall the definition of a standard GARCH PQ model. So it's a semi-parametric model here because the noise distribution, so the distribution of the ID process, eta t, is not specified. So necessary and sufficient conditions for the existence of even order moments depend on the moment of eta t, and they have been established for a long time. Some of these conditions are explicit. They can be obtained in algebraic form. So this is the case of second order moment, and also of the even order moments in the first order case. So in this graph, you have an illustration of the fact that for typical parameter values obtained in applications, it may be very difficult to know which moments exist or not. So here you have the different stationarity regions. So in the top panels for Gaussian innovations, so you have the second order stationarity, which corresponds to the straight line, and you have a region corresponding to sixth order moment or fourth order moment. And you see here in the bullet, the red bullet corresponds to the value of parameters. So you have alpha on the horizontal axis and beta on the vertical axis, which correspond to a typical value encountered when you estimate such models. And what we see is that the point is very close to the boundary of each stationarity region. So we may anticipate some difficulties when testing such conditions. On the bottom panel, you have a similar situation with student innovations, student with 7 degrees of freedom. So the first step is to estimate the model the parameters of the model, and here we use the most widely used method for such models, so the Gaussian QML estimator, which rely on this type of criterion. And the assumptions for the consistency and asymptotic normality are mild. In fact, you have essentially a strict stationarity condition through the top-Lyapunov exponent. And you have also some moment condition, but not on the observed process. You have a forced moment condition on the ID process. And no extra moment condition on the observed process, on the log returns process. So in this result, you have the joint asymptotic distribution of the vector of parameters, the estimator of the volatility parameters, and a vector of residuals, of moments, empirical moments of the residuals. So the residuals here are written eta hat, and you have this empirical moment of order R, which is defined here, and mu m hat is a vector of even order empirical moments for such residuals. So the joint distribution, as joint asymptotic distribution, holds with almost the same assumptions as for the distribution of the parameter, except an additional moment assumption, again on the ID process. So what is interesting here is that if you consider the asymptotic variance here of the, of the vector of empirical moments, so the coefficients of this matrix are completely independent from the parameter, the true parameter value. So we can say that it's model-free, as Christian defined in his talk 2 days ago, but it's not estimation-free. So there is an effect of estimation. The distribution would be much simpler if the innovations were observed instead of being estimated. So there is an effect of estimation, but no effect on the true value of the parameter. It only depends, these quantities here, only depend on the moments of the innovations. And this comes from this relation, this equality, which I like to present because it's not so much known. So with this relation, which can be established, we can see that the distribution of the empirical moments is model-free, in fact. And this equality can be obtained by considering the degenerate case where m is equal to 1. So when we consider a second-order moment, in fact, the second-order moment of the residuals has a degenerate distribution, and from this observation, we obtain this equality. So now let's consider the first-order model. So in this case, the even-order moment condition has a very explicit expression. And using the previous asymptotic result, it's straightforward to derive the asymptotic distribution of this quantity here, which corresponds to the moment condition. And so it's also easy to derive a test. So here we can consider two mth order stationarity problems. So under H0, the 2mth order moment exists, and conversely, you can test the assumption that such moment doesn't exist. So the test is also a straightforward consequence of the asymptotic normality result. So you have the test statistics, which is built on this stationarity condition. And you have a critical region, asymptotic critical region for the test, which is defined by this expression on the statistic Tn. Yeah. So what we need is a consistent estimator of the asymptotic variance in the asymptotic distribution. So this may be avoided using a bootstrap procedure. So I will not develop this point, but there are some slides at the end of the talk for those who are interested. So we developed a sampling scheme to avoid estimating the asymptotic distribution, and we show the asymptotic validity also of this bootstrap procedure. So as usual, when the null consists of an open set, the test is constructed for the closure of the null assumption. So the asymptotic region satisfies this equality, where the supremum is taken over all possible values of the parameter under the null and all distributions of eta t also. So now I will consider alternative version of the QML estimator, which may provide efficiency gains, in fact. So even if the Gaussian QML is routinely applied in estimation, it may have interest to consider alternative QML estimators. So this is based on the multiplicative form of the model. So epsilon t is written as a product of the volatility and an innovation process. But instead of the standard unit variance condition on eta t, you can set any other moment condition eta t. So, for instance, you can impose a R's order moment equal to 1. Because you have to avoid the identifiability problem. If you don't constrain eta t, you can multiply eta t by a scale and change the parameters. So you have to impose something which can be a moment condition of this form. So doing this, you also modify the parameter value. So it's no longer theta 0, but a theta 0 depending on R, which is related to the previous original value through this linear relation. So the beta coefficients are not modified, but the other coefficients are scaled. So likelihood, maximum likelihood estimator, quasi-maximum likelihood estimator can be defined, but not using a Gaussian density for the criterion. It wouldn't lead to a consistent estimator. But if you consider this kind of criterion, so it's very similar to a Gaussian criterion, but with power R for the absolute observations, then with almost very similar assumptions to those generally used for the Gaussian QML, you can establish consistency and asymptotic normality of the estimator. But of course, if you are interested in the original value of the parameter, you have to rescale the estimator to obtain a consistent estimator of this original value. So here we have the asymptotic distribution of the corresponding QML. And it depends heavily on this function g of R, which involves moments of the innovations eta t. So the Gaussian QML corresponds to R equal 2, and we retrieve the usual form of the asymptotic variance. So, for instance, considering the testing second-order stationarity problem, this assumption, which here is simply that the sum of the alpha and beta coefficients is less than 1, can be tested using this generalized QML estimator. And we have this statistic, which depends on the corresponding non-Gaussian QML estimator. So how to compare the different tests that can be constructed using these QML versions? Here we consider local alternatives of the null assumptions. So we have this value theta n defined through this direction tau. Here we have p plus q plus 1 per components, the parameter. And with some regularity assumptions on the density of the innovation, we can obtain, and also the land property, which has been established for GARCH by Drost in particular, a long time ago. We can derive the local asymptotic pairs of the second-order stationarity test. So for different values of R, in fact, the tests differ essentially to this coefficient, sigma R. So the smaller this coefficient, the more powerful the test, in fact. So we just have to minimize this quantity if we want to obtain the more powerful test in this sense. We have to minimize with respect to R, because we choose the parameter constraint, this quantity. And so we can define when there is a minimum value of, called R0 here on a given interval of values for R, we can see that the more powerful test within this class is obtained for this value of R. So in fact, this R0 depends on the errors distribution. So if you have a Gaussian, true underlying Gaussian distribution, the optimal is, of course, the maximum likelihood estimator. So you obtain R0 equal 2. But for other distributions, for instance, the student distribution, the value of R0 will be smaller. They can be smaller than 1. Another remark is that the minimum of this function G may not exist for particular distributions of theta t. And last remark, this quantity is not known, but it can be consistently estimated by minimizing an empirical version of this quantity. So I present a few numerical illustrations before turning to the augmented GARCH case. So here we have some simulations for the existence of two mth order moments. So this is the model we consider. So for this parameter value and this distribution of the errors, the stationarity constraint, so given by this quantity and negative here, so this constraint is satisfied up to m equal 2, so fourth order moments. But for m equal 3, we are exactly almost at the boundary of the stationarity assumption. So moments of order 6 don't exist, in fact. So when we simulate and estimate this model, we can see that the powers are satisfactory, also for values of m less than 2. But on the boundary of the null assumption, we are a bit below the nominal size. So the test is too conservative. So by considering a bootstrap version of this statistic test, we improve the results, in fact. And also, if we consider tests based on a non-Gaussian version of the QML, so here we minimize this quantity. In first step, we estimate theta, and then we can estimate these moments of the innovation and apply the QML version. So we have in this graph empirical estimates of this function g of r. And so here it's drawn for a Gaussian distribution. So the true value R0 is R0 equal to, which minimizes this function. And we see that on the empirical versions, we are not far from 2 in general. But also we have to be careful because if we minimize over a too large set of values, in fact, we might be below 2. And more precisely, we can show that for fixed n, as r goes to infinity, this function goes to 0. So that's why you have to perform the minimization of a not too large set of values. And indeed, when we apply this generalized QML, we improve the results in terms of control of the size, essentially, also the power. Just an illustration on a real data set. So here we have a stock over more than 4,000 observations. And we can see that when we consider the test statistic, Tn, we have here the different values. So for m equal 1, we have clear evidence that the moment exists. And we have some evidence that so m equal 4 corresponds to 8th order moment don't exist. But for m equal 2 or 3, the test is not conclusive. And, okay. I will now consider other more general forms for the volatility dynamics. So in fact, many GARCH-type type models can be written under the following form. So you have this power delta for the volatility and some function omega and a of the innovation process with lower bound for this function. And of course, the standard GARCH and many other formulations enter in this class. So the strict stationarity condition is well known for this model, and also the existence of moment is known. We have this condition. So it turns out that the existence of U delta moment for sigma t, and also for epsilon t, the absolute epsilon t, is equivalent to this condition on the autoregressive function A. So this function, as a function of U, can be called moment-generating function of this model. And so now if I consider a parametric version of this model, so let's make the functions omega and a depend on some parameter theta 0. We have to define, to handle the problem of initial values, so for any value of theta, and any initial values, we can construct recursively this sequence. But of course, this sequence is not stationary and ergodic, so you can approximate this sequence by the solution of a stochastic recurrence equation given by this, provided that there is a solution. So we need conditions ensuring the existence of a solution to this stochastic recurrence equation. And this is given by condition B2, so a sufficient condition for the existence of such a solution. So the other assumptions are strict stationarity, and B3 means that the initial values don't matter asymptotically. So it's also a condition which is satisfied for most typical models from this class, most classical models. So in this case, I will not consider particular estimation method. So let's instead assume this Badger expansion for the parameter estimator. So it's not necessarily QML. It could be ML or any other consistent method of estimation of the parameter. And we have this expansion for the parameter. So here there is a function of the independent process, and here something which depends on the past value of the process. So it's natural to introduce this statistic because you recall this function, hence infinity of u should be less than 1 for the existence of u's order moment. So the empirical version is given here, and we have the asymptotic distribution for this test statistics. So here it's not independent from the model. Everything depends on theta 0. But in the particular case of a standard GARCH, you can obtain more, and also for the QML and ML, you can obtain more explicit asymptotic variant. So the main difference with respect to the first part of the talk is that here the power u can be a real, any positive real. So it's not only limited to the integer powers of the volatility. So u is only a positive number. So we may test again the stationarity, the existence of u's order moment through this condition. And so again, the test statistic follows straightforwardly from the asymptotic distribution for this statistic. But there's another way to consider the same problem through the maximal moment exponent. So it was considered in particular and studied by Berkes and co-authors for the standard GARCH 1.1. So it consists of the maximal order u0 at which moments of sigma t to the power delta exist. So it's also the maximum order u such that this expectation is less than 1, strictly less than 1. So here are some graphs of this function. So it can be shown that it's convex, but the minimum, we need some conditions ensuring that this function crosses the line corresponding to expectation equal to 1, in fact. So when typically in the second case in these conditions, when the support of this function r theta t is not included in 0, 1, and if you have this moment condition, there exists some s, positive s, such that this expectation is finite and greater than 1, then there is a unique such maximal moment u0, in fact. And so the testing problem can be written in terms of this coefficient. So in this result, there is the estimator of this coefficient. So we have an estimator, again, based on the empirical version of this statistic here. So we take the maximal value, u, such that this statistic be less than 1. And I don't present all the assumptions here, but depending on some assumptions, which you can find in the paper, we have consistency and asymptotic normality of this coefficient. So a test based on this empirical maximal moment estimator can be given here. And you have these statistics if you want to test that u is less than this u naught, so the maximal order. So it means that you are testing the existence of moments of order u positive. Then you can build a test based on these statistics. It's a consequence of the previous result. How much time do I have? Am I over already? 3? So when the density is known, so to have a comparison, we can compare the different estimators with the ML estimator. which can be used when, if you are ready to assume that you know the density of the errors. So in this case, the MME can be obtained by solving this equation. And similarly, for the estimator of this coefficient, so you obtain the asymptotic distribution of this coefficient using an assumption for the ML estimator, which also is obtained in the paper by Berkes and co-authors. So this statistic, based on this estimator on the MME, so is given by this quantity, so VNU, and under the previous assumptions, we have these critical regions for the tests. So power comparisons can be done. Again, so finally we have three statistics in the case of, for testing this assumption. So based on the empirical moment generating function, you have the statistic T. Based on empirical MME, you have U, and if you have a fully parametric estimator, you have another statistics. So comparisons can be done, again, using local alternatives. And what we obtain is that the first two statistics have, in fact, the same asymptotic powers, while the statistic based on the knowledge of F has a different power, in general, superior power. So it can be illustrated on this graph where we have, as a function of tau, so the departure from the null assumption, you have the different powers corresponding to the three statistics. So I think I will also provide some alternative comparisons based on Badiou's slopes, but I will not develop this. So I think I'm already over. So just a few words of conclusion. So we have seen that tests based on the QML are valid whatever the distributions of the innovations, and we can improve. So this was for the first part of the talk, by choosing appropriate versions of the QML. So improvements come from bootstrap versions of these tests, and also we can obtain locally optimal tests by considering these different versions of the QML. So if you have a power which is not an even number, you can consider in the augmented GARCH framework a test based on the alternative statistics that I proposed. But to come back to the initial motivation on financial time series, these numerical results suggest that we have to be cautious in assessing the existence or non-existence of moments for such series. So, thank you, and there are a few references here.
Okay, thank you very much, Jean-Michel. Perhaps we're going to for questions from abroad. Are there any questions? No. Okay, so perhaps some question in Marseille. Okay, here.
Have you checked if with your augmented GARCH model you were able to actually conclude on the existence of the 4 or 6 other moments on the classical GARCH-11, because it wasn't conclusive for the classical GARCH-11 model, but since you can test for like uneven moments, have you checked?
No, in fact, the second part of the talk, as I said, is ongoing research, so I didn't present any numerical results for the second part. So for the moment, we don't have such conclusions.
Thank you. Another question here.
Hi, Jean-Michel. Thanks for your talk. I have some questions and remarks, but maybe we can talk also later. First, I would like to go back to your slide with the invertibility condition. And I was thinking that it would be implied by a Bougerolles theorem from the existence of the solution of the SRE. So what do I miss? Is that you miss the uniformity in theta?
Yes, for the condition B3 we have uniformity in theta.
Okay.
So it's not a consequence of B2, which is for particular theta.
Okay.
Yeah.
Okay. My second question is about the alternative. So you always talk that the alternative is the fact that the moments would be infinite.
Yes.
Could you try to think about an alternative where the coefficients would not be constant, something like a break of stationarity, and because we know that there are some works of Stroman and Mikos saying that if you have a break of stationarity, then you will also, even if the two, let's say if the two sets of coefficients satisfy alpha plus beta smaller than 1, it might be that on the overall period, this condition is not satisfied because of a break.
No, in this presentation, the maintained assumption was that the model was correctly specified, in fact. So even under the alternative, we don't have breaks or Markov switching. But it would be interesting, of course, to see how these tests perform in such case. But
as a final question, I would say that, or remark more, or suggestion is that, so you as I understand, then you try to let's say estimate the moment generating function, so that to find a route to that one, and you could use you have a lot of strong convexity property on this moment generating function. You could use that to
yes, probably
because for instance you know that it's strongly convex, and so you know that it can't go down for n. So you could for instance try to estimate the, I don't know, maybe the second derivative and.
Yes, exactly.
Yeah,
I agree.
Okay.
Good suggestion.
Thank you.
Okay, so perhaps we stop with questions and thank a lot Jean-Michel again.
Thank you.